So we're going to focus on 4.4 today. This is basically taking all the info we have so far that we've developed and trying to intelligently figure out what some of these functions look like. And let me give you one right here. Now there's another kind of thing that we can kind of bring to mind here. By the way, when I look at these functions, your book in this section here, you will find at the beginning of this, they give you graphing outlines for f of x. Number one, identify the domain. Number two, exploit symmetry. Number three, first and second derivative. You get this nice list. Right? Just you want to know what the function looks like, don't go through somebody's little robot procedure, right? Let's look at this and see if we can figure out what important thing is. The first thing that there's kind of a lookout point on this, right? There's kind of a danger point. What catches your eye? Right, you're going to have some kind of funny business going on here the next step. Everybody agree? What do you suppose it is? I would think it would probably be a vertical asymptote, right? Because as x is getting close to 2, the denominator here, or outside the numerator is getting close to 4, the denominator is getting close to 0. So this is getting huge, either positive or negative. Everybody agree with it? But besides that, the domain of this is everything except for 2, right? So this should be continuous and everything. Let's take a derivative. And actually, there's a little algebra. And some probably algebra is useful. Everybody at some point, 5 and 12 numbers. Going to put this down on the back. So keep my place. How many times does x go into x squared? You got to multiply x by x to get x squared, right? I agree with it. So multiply this becomes x squared minus 2x. And just like you were doing old fashioned on you subtract. Right? X squared minus x squared is 0. 0x minus 2x is 2x. And how many times does x go into 2x? 2 times. Okay. Kind of the same thing. It's 2x minus 4, and you subtract 0 and 4. So I would say 2 and then 4. Because x doesn't go into this. Right? Everybody agree with that? What does this mean? Well, this means that actually another way to write this function is convenient for a couple of things. For a couple of reasons. This is x plus 2 plus the remainder 1 by 1. By the way, you can always check this by finding a common denominator, and in fact, you should be back at the start. Somebody agree? This actually tells me something about the function. Can you write that in? What this demonstrates? What happens? What does this function look like when x is very, very big? See this fractional piece here? What happens to this fractional piece when x gets very, very big? This is almost what? What's the limit of this thing? As x goes to infinity. It's fractional. As x goes to infinity, I just need a problem here. The limit as x goes to infinity 4 over x. What else that one x goes? Oh, it goes to 0, right? 4 over 10 million, 4 over 10 billion, 4 over 10 zillion, right? It's getting very, very small. Do I agree with that? That means that this function looks like line x plus 2 when x is very large. So it should be getting closer and closer. That actually tells me something. Because I don't know what this function does. In the middle, it might wiggle around quite a bit. But the line x plus 2 goes like this. Whatever this function does in the middle, it eventually gets very close to that line. That actually tells me something. This is often the large term behavior. If you're an engineer, sometimes you want to know what's happening to things when time gets very large, for example. And this gets very close to this. This also, in a certain sense, makes taking the derivative a little bit easier. Taking the derivative of this, I get 1, and this is 4 times x to the minus 2 power. I get that. And the second derivative, that goes away, and I get what, 8 over x minus 2. Because that's minus 4. So it'd be 8 x minus 2. Okay, let's analyze the derivatives, right? Let's look at this one first. If I look at 1 minus 4 over x minus 2 squared, where is that undefined? That's undefined for x equals what? 2. Can somebody tell, it's actually not a critical number. So you why it's not a critical number? Right, and you can't plug it into the original function, right? But it's important nonetheless, because the derivative change sign there. So I'm going to put that, I'm going to record this later. So this, I get 4 over x minus 2 squared is equal to 1. This gives me 4 is x minus 2 1 squared. So I get x minus 2 is equal to plus or minus 2. So I get x is 0 and 4 done. So for the first derivative, there's 3 points of interest. There's 2, which makes that denominator 0. And then there's 0 and 4. One minus. Yeah. So I've got 3 points that I need to report. 0, 2, 4. And I want to figure out what the sign of this is. Okay. This is actually rather easy to check because these 3 points, these critical numbers and pseudo-critical numbers, these are the only places where the derivative can change sign. Right? Because these are the places where the derivative is either 0 or does not exist, right? Everybody okay with that? The only place that can change sign. So if you're less than 0, what's the sign of the derivative? Somebody give me a convenient number. It's in this range here. -1. Plug in -1 here, and I get 4 over, see, not minus 2 squared. 1 minus 4/9 is positive. All you gotta do is check one number in that right. Another way to see this is notice this range goes all the way over here. As x goes to infinity, this piece goes to 0 and positive. What's a convenient number in this range? How about positive? Let's see, I get one minus, see, one minus two, that's one square, so one minus four, so that's negative. What's a convenient number to check here? How about three? Three minus two is one squared, so one minus four is, again, that's negative. So it doesn't change signage across two. And what's a convenient number to check here? How about 100? 1 minus 4, 98 squared is very large, so 1 minus very small. That's positive. Now, what happens here? This is a local max. Right? Goes up and that should occur at 0, 0. This is, I think this is an action point. We were talking about that earlier, that x equals 2, this doesn't exist. And this looks like it's going to be a local min. It occurs at 2.4. Let's see, 16 over 2 is 8. Funny, isn't it? Your max is lower than your min. How about concavity? That's actually even easier to tell. It's got 8. There's only one place where this sign. That's the basic. Remember again, too, is where I think that aspect. So let's analyze the second paragraph. What happens if you're bigger than 2? Something like, I don't know, 3. This is 8 over 1. Positive. What happens if you're less than 2? Something like 0. You get 8 over a negative. That's negative. And so this, what do we call this? What does so mean to you? That was a trick question. The concavity does change there, but there is no point to it. So when it crosses the asymptote, there will be a change. This is concave down. All right, so I've got what I think is a reasonable sort of picture of this. Let's see. Well, let's see, I've got this local max at 0, 0. I've got a local min at 4, 8. I'm not going to take very scale on this. Then max. And I think I've got an asymptote here sort of halfway in. And just for giggles, I'm going to put the line y equal x plus 2. So I'm going to call this line x plus 2. Now, what happens to this function? Before the asymptote, that is, when you're on the left side of the asymptote, this increases, hits that local max and decreases, all the while staying down. So, not even draw this very well. This is supposed to be getting closer to the line. And what happens over here on this side of the asymptote? Well, it decreases till it hits the local min, then it increases, always staying concave up. So it should come in this. Draw this back. And that's supposed to be man. It's closer and closer to the line. Notice that this thing is under the line here, right? Think about what this means. This function, another way to write this is the line plus this little arrow, right? Here, over in this range right here, x is negative. So the actual function that I'm drawing solid should be the line, and then you take away a little bit. So it's below the line. Over here, the function that I'm drawing solid is the line plus, now x is positive, it's actually above. Everybody see that? Any questions? Okay. Let's try this. X to the 1 third. Okay, any questions? Okay, for the next one or two, I'll give you this and the derivatives too. That's the way the quiz is going to. Quiz is structured today, just like the one that you had Friday. I'm going to give you the derivatives because I don't want you making a little mistake and having to turn it into a disaster. Okay. So this is function 1 and prime of x is equal to x to the 1 third. Natural log of x squared minus 6 over 3 log of x squared times x, and have double prime of x is absolutely horrible. I did give you a hint on this one. Minus 2x to the 1 third times log of x squared minus 3 log of x squared minus 36 over 9 log x squared cubed times x squared. And the roots of the top and then I said roots of are plus or minus 0.1 and plus or minus 0.6. So I told you what the roots of those two are. So let's see if we can get this figured out. So I've told you the derivative, but we still want to figure out all this mess here, right? So let's do this. Let's sort of figure out what the roots are. First. All right, look at the function here. What's the domain of this? What can you plug in and you're good to go? You can plug in every real number except for three problems. You know. What do we got to throw out? Zero. You got to toss zero. And because zero, you can't even plug that into the log, right? That's why that's off the table. Everybody agree with that? Now, the second thing I would think about is I don't want that denominator to be zero, right? Where, what value of the log, when is the log zero? Log of blank is zero. One, right? And so you don't want that x squared to be one, right? So you don't want that x to be plus or minus. But everything else is good to go. I agree with that. Now, these numbers should factor into all of your, when you make that little sign chart, these numbers better come in with regard to both the first and second derivative. What else comes out of this? Well, extra critical numbers. I get x equals 0, but I've already got that. I've also got log x squared is equal to 6. Let's say you make that 0. So I get x equals plus or minus e cubed. And then I get x equals 0 and I get x equals 0 plus or minus 1. So I don't get anything new out of this, right? Because how can I screw up the bottom? I can make x 0, I've already got it. Or I can make that thing 0, I've already got it. Everybody okay? Now, so I'm also going to need x plus or minus e cubed here. What about down here? Well, make either the bottom or the top 0. Well, 0, I've already got it. Oh, this can be 0. And I've got this. And there's nothing new out of this either. So now I've got everything we need. So let's do an analysis of the first derivative. I'm going to have my 0, 1, minus 1, e cubed, minus. By the way, let me point out, this thing is always positive. Agree? Because you're squaring. So when I'm trying to figure out the sign of this, yes, I don't have to consider it. It's always positive. What happens, let's say, when you're to the right of EQ? Very, very large number. Well, that's going to be positive because x is positive. And actually, you know what I can do here? If I did this right. Can anybody? Yeah, looks like you can do that. There's a way that I can simplify this and make this a little bit better. Can anybody tell me what it is? I can actually cancel this, write this section 30. Display coming line. That makes it easy. Perfect. Notice x to the 2/3 is also positive. So now my whole bottom is positive. So and this piece is gone. So all I have to worry about is whether this is positive or negative. Now, when you're to the right of E cubed, something like E to the 4th, well, that's going to be log of the A. That's going to be positive. And the same thing on the other side here. Because you're squaring a number that's sort of magnitude. Now notice the sign changes at 0, they're all encapsulated in here, so they don't matter. So actually, log the solution to this, the plus or minus E cubed controls the sign. When you're in the middle, it's always negative. Because in between there, this thing is always negative, and these things are always positive. So I am increasing, decreasing, 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 increasing, increase. What happens here? It's a local maximum. And here, yeah, local man. This one is an E cubed, or whatever I give them, put in E cubes here. This should be E on the top, and this should be 6. So this should be something like that. E over 6. And this should be minus E over 6. By the way, what are you supposed to happen is that 1. I would think, let's think what was happening here. 1. Numerator is getting very close to 1. 3. What's happening to the denominator? It's getting closer and closer to log 0. So what's that? And there is no log 0. What happens there? Right, negative infinity. So 1. So what are you supposed to say? Because log's getting big. Or I'm sorry. This is getting, if you're getting close to 1, this is getting close to 1. This is getting close to log of 1. So this is actually getting huge. Everybody agree with that? I think probably both of these have vertical aspect. What happens at 0? What happens when you get close to 0? What's the numerator getting close to? Numerator getting close to 0. What about the denominator? Yes, yeah, that's right. So it's getting very, very large. So you got a small numerator, huge denominator. It's getting close to 0. This is another good one for let's look at the limit. As x goes to 0 of x 1/3 over natural log of x squared. Be careful. This one is not appropriate for local algebra. It's 0 over infinity. There's no, it's not infinity over infinity, it's not 0 over 0. This one is 0. Because numerators get small, denominators. Everybody okay with that? So here you're getting close to 0, 0. But not quite there because 0 is not done. What about the second derivative? This one is pretty dang awful because you have not the scale 1 minus 1, 0 minus 0.1. Zero minus 0.1, 0.1, 1 minus 1, and minus 46.1, and 46. Not the scale. Now, this one is much, this was a tough analysis. Notice this piece is, I guess I could cancel this 1/3 again. Which might be. I'm going to do that. Let's put down 5/3. Now, what happens? What happens when you're well beyond 46.1? Like huge number, right? Well, that's going to infinity and it's squared then. So it looks like this is going to be positive. That kicks in as negative. Huge positive number. This is going to be positive. So it looks like a grand total is negative. Right? Positive times negative. So in fact, it might help do this. You look at the log of x squared minus 3 log x squared minus 36. Let's just see what that piece looks like. Just this piece right here, because maybe this is the most. It is positive over here, positive over here, very long time. What happens? What happens when you're close to 0? Well, when you're close to 0, this is huge, and then you're squaring. This is huge. There's a square here, so it moves back. And what happens in this range? This range right here is easy to test out. Because all you got to do is put the next one, log 1 to 0. So 0, 0, negative 36. So just this piece behaves this way. All we got to do is see what else happens. Right. So in the range from 1 to 46.1, something like 2, we know that this is going to be positive, or I'm sorry, it's going to be negative, right? that's going to be negative, and something like 2 log of 4, that's going to be positive, that's going to be positive. What if something negative, negative, positive, positive? So, positive. What happens between 1 and 0.1? Well, this big chunk is still negative, that's negative, so I've got a positive numerator. When I'm less than 1, this is going to be negative, still positive, so grand total negative. How about really tiny, like even less than a 10, but bigger than 0? Well, if you're less than a 10, this chunk's going to be positive, negative. So I've got a negative on top. That's going to be negative, and that's going to be positive. So it looks like the grand total is positive. Okay. Let's look at this. What do you have? You have a very tiny negative number. Right? This piece right here is positive. Agree with that? Because that's what we figured out here. This piece is negative because it's negative 2. So I've got a negative number. Right? Okay, what about on the bottom? Well, I have a log of a tiny number, and a log of a number less than 1 is negative. So that's going to be negative. And the x itself is going to be negative. So I get 2 negatives over here. Negative over positive. What about in this range here? Say like negative 0.9. Let's see what happens with negative 0.9. Well, let's look at this piece first. Negative 0.9 is in the negative range, right? And that's also negative. So I get a grand total of positive on top of my fraction. Everybody with me? Negative 0.9 here, that's a log of something that's less than 1. So that's negative, cubed is negative. And that's going to be negative. So I get a positive on the bottom as well. Okay. Are you guys getting where I'm coming up with the signs? This is kind of important, so stop me if you're not. Okay, let's do this again. How about between negative 1 and negative 46.1? Negative 10, so. Negative 10. Well, if I look at this piece right here, negative 10 is in this range, so that's negative. That's negative, so I get a positive up here. Negative 10, that's a log of 100. That's positive here. So that's positive here, but negative here, right? Because that's an odd power, right? So, minus. So it should be a grand total of negative. And finally, what happens when you're to the left, negative 46.1, let's say negative 100, what happens? Well, in the negative 100 case, this piece right here is positive, and that's negative. So I get a grand total of negative up here. Negative 100, the log of 10,000, that's positive. That's positive, and that's negative, negative. Everybody okay? By the way, somebody give me a gut check as to why this is probably right. Look at the original function. This does have a certain symmetry to it. Does anybody know what kind of special type of function this is? It would be odd if you haven't seen this. Anybody remember what an odd function is? Remember that maybe from back in the day? Yeah, so let me kind of take that apart here. The original function is odd. What it means to be odd is f of minus x equals minus f of x. Some functions that satisfy that are odd are functions like f of x, x cubed, sine x, tangent x. These are all odd functions. And what this means is to get this function this way, basically, to get the other side of the function, if you know what's on the right side, this equation means to get what's on the other side, just turn this around, pull it over, right? So notice in this hump here, you were concave up, no, you're not, you're concave down, right? In the mirror image, you're concave up, right? Notice that here you're increasing up to this point, and here you're decreasing, right? And and notice that what happens here is when you turn this bit over and flip it over, the concavity reverses and the increase decrease is symmetric, right? So for example, notice after this point, it's decreasing. And up to this point, it's decreasing. Right? And this is exactly what we got in the sine chart. Right? Notice about 0, it's symmetric. Right? Increase and decrease. Both decrease, both decrease, both increase. Agree? And look at the concavity. It flip-flops. Right? This is concave up, and the corresponding piece is concave down. Concave down, corresponding piece concave up. Concave up, concave down, concave down, concave. Notice there's lots of points of inflection. I will highlight them. Notice concavity changes at every opportunity. -1, 0, and 1 are not points of inflection because these are two asymptotes. And this is not, and 0 is not even in the domain of the function. Okay, let's see if we can get what this looks like. Okay. Notice as x gets very, very close to 0, this gets close to 0, 0. We pointed that out. And I think I've got a couple of asymptotes at 1 and negative. Okay, so let's just take this apart. Let's go between 0 and that asymptote of 1. What happens? My function is always decreasing. It decreases down to the asymptote, decreases off the asymptote. It is concave up until 0.1, and then it's concave down. So we describe it when we say very close to. So I think see, it's got to be concave up, and then it goes concave down. So let's see what's that. Right. Yes. And it should be the same on the other side, right? So between -1 and 0, it should always be increasing. And it's concave up and then it's concave down at the last minute. Now, what happens beyond 1? Well, it's decreasing until it hits its local min here, and then it increases. And its concavity is up until it hits 46.1, and then it's down. So it should do something like this. Let's say this is e squared. It's got a local min here or here. There's your local min. It decreases off the asymptote. It's that local min goes up there. So it goes down and then up. But the concavity changes, like flattens out a little bit. So it comes down, it's decreasing off the asymptote, hits the local min, it's still concave up, concave up, concave up, concave up, and then eventually it goes way out here at 46.1. I always close these things. It's hard to draw a concave. But there you go. Now, when you take this, turn upside and flip it around, so it should have, I haven't got the whole thing drawn yet, but it should have something like this well on the other side, just from the fact that it's not a function. And let's see if we got everything that we need. It increases, decreases, 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 increases. And I put my concavity way out there in, put the concavity twice in there. Yeah, so that should be more of it. Okay. Any questions? There are other analyses that you can do. Let me ask you this. There's one thing about my picture that I'm curious about, and I certainly wouldn't demand this much subtlety out of you here, but let me ask you this question here. Let's look back at the derivative. Just for this example, the derivative was, let me simplify this. Log x squared minus 6 over, this is good L'Hopital's problem, 3 log x squared x to the 2/3, I believe. That's what we had when I corrected it, or when I simplified my derivative a little bit. Now, let me ask you all this. This is kind of an artsy little culture. I'm going to my question is, what is limit as x goes to zero? The way I've drawn it, it looks like it should be infinity, because what I'm asking here is what's happening to the slope of the tangent line equal to 0. Looks like I've drawn them so it becomes sort of infinite steep, right? But there's no reason it has to be that. It might be 2, or it might be, well, in this case, I guess it would have to be negative. But how do we figure this out? First thing to do would be a bonehead, plug in. Right? Log of 0. That's going to be negative infinity. So I've got negative infinity on the top. On the bottom, I've got negative infinity times 0. So I don't even know what the bottom is. Right? So this requires another problem. So first, I need limit as x goes 0, natural log x squared x. This piece is going to infinity. This piece is going to 0. Now, to use what we talked about, I need a fraction. What do we suggest? I think that's really the best strategy. So let's see what happens. This is minus 2/3 x minus 5/3. Right. And derivative at the top is 2 natural log x squared times derivative of what's inside, which is 1 over x squared times 2x. So this is when as x goes to 0, I need to clean this up a little bit. It's going to be 4 times natural log of x squared over minus 2/3 x minus 8/3. That 2 times 2 gives me that 4. Log x squared is here. I've got an extra 1 over x. So that puts an extra power of x in the bottom. Now, what do I get here? I get negative infinity over negative infinity plus this becomes 4, 1 over x squared times 2x over 16/9 x minus 11. And this is equal to that's 36. That's 9/4. That's 1 over x, so that's going to be x minus 14. 1 over. So it's 0. Oh, this one might be easier. So what happens to this? I was worried here though, so we do a little bit of algebra, but I don't. As x goes, it's closer and closer to 0. That top is going to negative infinity. Right, Brady? Top huge, right? What's happening to the bottom? Going to 0. What happens when you take, and in fact, not only is it going to 0, it's always sort of positive. So what happens when you have a huge negative number divided by a small positive number? It's an even bigger negative number. This is actually negative infinity, both sides. And actually, you can see this. The source of the tangents go to negative infinity here. So there's lots of ways to now analyze this more and more so. Any questions? Questions? Okay, let's do another one. How about this one? Let's do x over x squared. Okay. First thing to note, I got a couple of problems with this one. Where do they show up? What are some numbers to look out for? One and -1, there should be some funny bits, right? So the domain, everything except for plus or minus 1. And notice as you get very close to plus or minus 1, that numerator is getting close to plus or minus 1, and the denominator is getting very, very small. I think that there's going to be vertical asymptotes. Vertical asymptotes. Okay, so I've given you the derivatives. The first derivative of this is x squared minus 3 over 3 times quantity x squared minus 1 to the 4/3. And f double prime of x is minus 2x times x squared minus 9, 9 x squared minus 1. Okay, so what are the critical numbers for? Well, they're the numbers that make this either 0 or undefined that are in the domain. So I get x is plus or minus square root of 3. That makes the numerators here, right? And that'll be where I expect there to be. I expect there to be horizontal tangent lines here, and also, and I'll put this in red, plus or minus 1. I put those in red for 2 reasons. Number one, they're not in the domain of the function, so you can't plug anything in. But I think they're asymptotes and change signs. So I need to. How about the important numbers here? Well, it looks like I get 0, plus or minus 3, and again I get plus or minus 1 because the sign could change for the concavity. Everybody feel like they can get those numbers out? Yes, sir.
So just to clarify, first, the second prime, that was 7 zeros.
That's right. And the way you make the 0 is either this piece of 0, which means x is 0, this piece of 0, which is x is plus or minus 3, or the bottom 0 plus or minus. Everybody clear on where all that came from? Okay, so let's analyze this. let's see, the first derivative, I get minus square root 3 minus 1 square root 3. All right, I've got a little helping hand here. Because this piece right here is always positive. Right, because it's the 4/3 power. Everybody agree? So for the first derivative, the denominator has no bearing on the sign of the derivative, right? It's completely controlled by the numerator. Everybody agree with me? And the numerator has roots here and here. Basically, these two roots ain't gonna come in. In between radical 3 and negative radical 3, say like 0, and this thing is going to be negative. And outside the range, it's going to be positive. Now you can test the individual ranges here, but that observation shortens my word. This means since the numerator controls the sign, just find where it's positive and negative. It's negative when you're between radical 3 and minus radical 3, and it's positive outside the. So my function increases, decreases, decreases, decreases. And it might be worth reporting here. Let's see, I think these two are asymptotes, up and down, so this is a local max. And it occurs at minus radical 3. Whatever I get my plug in minus radical 3, which is something like minus radical 3 over the cube root of 2, whatever that is. Everybody's favorite number. And I get a local min. I plug in radical 3 over cube root. I don't care about scales. So I know that I get a max and min, a couple of asymptotes, looks like. All right, so how about the second derivative? Well, let's see what do I get. Minus 3, minus 1, 0, 1, 3. Now let's analyze this. Okay, this is a good practice one. It's not terribly hard to do, but it's good to kind of analyze the text. What happens, let's say, when I'm to the right of 3, something like 4. 4, this is negative, positive, so I get a negative on top. And I get, well, that's going to be positive. So the whole thing is negative. Everybody follow that? Okay, let's look at this range here. Between 1 and 3. Let's try 2. We'll have 2. I don't need the numbers, I just need the signs. X equals 2, that's going to be negative, negative, so it's positive. And then 2, that's going to be positive. So looks like everything's positive. Questions on that? How about something between 0 and 1, like say a half? Again, don't need to take them, just need the sign. When I plug in x as a half, I get negative. That's going to be tiny minus 9, so that's going to be 2 negatives, positive. When I plug in a half here, that's going to actually be negative. And it's not a power of negative, so it's negative. Okay. The whole thing should be negative. How about something between? How about something like minus 1/2 here? Well, that's going to be positive, negative, so negative. And that's going to be negative. And this is going to be positive. How about negative 2? Positive, negative. That's going to be positive. and something very, very negative, like negative 100. Positive, positive, positive. So concavity switches at every option. Let's see here. Looks like I've got a local max. And the only thing I really noticed about this is the local max is actually negative, so it's up in here somewhere. Mirroring local min. I think I've got these asymptotes of plus or minus 1. All right. Let's see if we can figure out what happens between the asymptotes and minus 1. Between minus 1 and 1, it's always decreasing. The function is actually 0 and 0, so that's got to be the benchmark. So between minus 1 and 1, it's decreasing, and it goes from concave up, and there's a concavity change down, right as I pass through the origin. And so I guess it's close. I think that captures what I want. It decreases off the asymptote all the way down to the other asymptote, always decreasing this range. Concave up, concave down. Smiling. Everybody okay with that? Okay, let's look at it from the asymptote here at 1 on forever. It decreases off the asymptote to this local min, which I have up there, and then it increases. Concavity wise, it is positive off the asymptote. And then once it passes this, some point, it starts to be rounded. So this, nobody's very happy. So man comes up in about 3, it changes like that. I guess so we're kind of mirroring this thing here. It increases and it's concave up until it's smiling until maybe 3, then it's concave down back together. So the scale very well concavity change part of it here. And probably about like any questions? Yes. Just think about it. Everybody see how to analyze it? Yes. Which one is it? Oh, I put it into the original functions, like that. Oh, so for example, this one right here. Okay, so when I put in x equals radical 3, I get radical 3 over the cube root radical 3 squared minus 1, and this is 3. 3 minus 1 is 2. I get radical 3 over the cube root of 2. So I don't care. I couldn't care less. My scale sucks here, but I think I've sort of captured what this thing should look like. And the most important thing about this local max that I found is really just that it's, the local max one right here is actually under the x-axis. Okay, any questions? Okay, actually, this one's. Any questions for him? Eli, you okay?
Yeah, I have a, how do you do the critical numbers?
Oh, I'll look at this in chunks. One way to get a critical number is to make the numerator zero. That's where I get my plus or minus right. Another way is to make that denominator zero. That's where I got my plus or minus one. Now, this one is technically not a critical number because it's not the domain of the original function, but you still need to record it and see if there's change. The same crap happens here, right? Make that zero, x equals zero. Make that zero, x is plus or minus three. Make that zero, make it plus or minus. Is that
Yeah, it was just confusing, like, I had problems with it. But like, I was confused. But we didn't.
Oh, yeah, we did. I probably did. So like the EQ, that's, you're kind of curious where that came from. So just like that, I set all those pieces equal to zero. And I had something like this. Right? And this means that log of x squared is equal to 6, right? Now I took the exponential of both sides. Right? And now it's the square root. So it's the same principle solving. And the ones that were too hard to solve, I just gave you the proofs. By the way, let me give you kind of a little one before we do at least one more. If I ask you to solve this, would y'all do it? In a pinch anyway, right? Everybody try to quadratic formula. Actually, let's do this. So if I actually find all real roots of this, then you go, yay. 1 plus 4, 2. Everybody good with that? What if I actually solve this? This is actually quadratic too. And if it makes it easier to wrap your head around, just change the variable. So just like before, I'll get u is -1 plus or minus the square root of 5 over 2. This is x squared. So how many solutions does that? In this particular case, it's only 2 because notice with the plus root, this is actually a positive number. Right? Square root of 5 about 2. Right? With the minus, there is no square, right? So the roots of this are x plus or minus the square root of 1 minus 1 plus 5. Now, if both of these roots had been positive, you would have had 4 answers instead of this. Okay, let's look at this one right here. I like this one. X to the and I've got 1 minus x squared. Now let me go ahead and derive this here. The first derivative is 1 minus 5x squared over 3x 2/3 minus x squared 1/3. Two is 5x4 minus 8x squared minus 1 over 9x5 times 1 minus x squared to the 4th. Now, you guys can work together if you like, whatever floats your boat. But what I want to do, I want you guys to try to figure out what the critical numbers are for this. Tell me what the domain of this, what the critical numbers are. And I use that term loosely. I mean, actually, first and second. Take a moment to see if you can get that. What do you all got? How about the? By the way, what's the domain? Can you plug in, look at the original one? You plug in 0 there? How about 1? I don't know. 0, 2/3, right? Because the powers are all positive. So notice if I plug in 1, I'm gonna get 1 times 0. Plug in -1, -1. I'll plug in 0, I get 0. So actually everything's in the domain. But you're right to single out that there's some funny bits going on at 0, 1, and -1. They just happen to be in the domain of the function. But there's strange stuff here. So critical. Critical numbers. I have 5 of them. What you all get? Okay. X equals 1. Okay, plus or minus. Something like that. What else? Agreed. And right, I'm gonna put those in red because, as Faith pointed out, something funny about it, right? I don't expect that 0 slope tangent. In fact, the derivative actually doesn't exist. So at these 3 x coordinates, +1, -1, 0. These are functions these are points that I can plug in the function, but the derivative doesn't exist. So I expect there to be funny bits going on. I expect there's a number of things that can happen. It could be a jump, but I doubt this because this function should be continuous. So I would expect there to be like a cusp pointy thing or a vertical tangent. Right? And I think that let's see. Well, we'll see what. And important numbers here. I'll let you this. What was it? Just a smidge bigger than 1 and a little bit less than -1? Well, let me get the easier out of the way. Again, I'm going to get 0 and I'm going to be plus or -1 here. How many roots did you get for the top? I got 2 as well. It probably wouldn't hurt us to go through that. This is the most complicated part of it. So I'm looking for places where 5 x to the 4th minus 8x squared minus 1 is equal to 0. Because that's the way I look for those places where it can change sign, right? And so I'm going to do that trick I did before. I'm going to let u equal x squared. So this is 5u squared minus 8u minus 1 0. And this brings me to the quadratic formula. So that's 8 plus or minus the square root of 64 minus 4.5 and minus 1. So this is 84, 8 plus or minus square root of 84 over 10, which is 4 plus or minus square root of 21 over 5. And 2 there, pulling 4 out of that, right? This gives me something that's a little easier for me to wrap my head around. Notice that 4 minus radical 21 over 5 is negative. So I can't take the square root of that, so those are out. Right, because the square root of 21 is bigger than 4 and it's less than 5, so that's a negative. Right. So I get u is equal to x squared is 4 plus square root of 21 over 5. So this is like maybe ballpark about 8.5 over 5. Then I've got to take the square root of it. So this is just a number. It's a little bit, the positive one is just a little bit bigger than 1. The negative one is just a little bit smaller than negative, right? So I'm going to call this alpha plus or minus. Because I don't want to write down stupid approximations all the time. It sound like this. So for the first derivative, I get critical numbers here. That's roughly, it's a little bit less than half. So it's minus 1 over 5, 0, 1 over 5, 1. Notice this piece is always positive because it's an even power, so it's not going to affect the sign. What happens? Let's see, when I do the right of 1, something like 2, it's going to be a negative top, and it's going to be a negative, and let's see, cube root of a negative bottom. This should be positive. What about something that's very, very close to 1, but a little bit less than it, like 0.9, say? That's again going to be negative. And this is going to actually be positive. So change the sign. How about something very, very close to 0, but still positive? So it's close to 1. So no complication there is positive. And this is positive. So it looks like it's positive here. How about something that's very, very close to 0, but it's slightly negative? Minus 1 over a million, so that's close to 1, so it's positive. That's close to 1, so it's still positive. Here, like symmetric. How about something in this range, very close to minus 1, like minus 0.9? That's going to be negative. That's going to be positive. Negative, positive, so it's negative. And finally, how about something off to the left here, negative 10, say? That's certainly negative. That is negative. So it's positive. So it looks like the function increases, decreases, increases, increases, decreases, increases. And so at my critical numbers, I get lots of interesting things going on. This one is a local max at minus 1, whatever I get when I plug in here, 0. This is a local min at minus 1 over 5, and whatever crazy crap you give me to put that in here. And what I can say about that crazy crap is that's positive, that's negative, so it's negative. So I'll just say something. We'll see how accurate I need to get it. 0 is a local nothing, right? You get to 0.00, but it's not extreme. This should be a local min, a max. at 1 over radical 5 and now positive. Where you can put that in. And this should be a local min at 1, 0. So there's lots of extreme action there. And finally, let's see what do we get here. I get now 0. I get 1 minus 1. And then I have that alpha. That crazy thing, just a little bit above and below here. Let's see what I get when I analyze. Let me do what I did before. This thing right here is positive when x is between minus alpha and alpha, where the roots are, and it's negative here, and positive otherwise. So this big piece right here, which is the most intimidating, is actually positive, or I'm sorry, negative in between here and positive outside of it. So let's see what happens when you're to the right of alpha. If you're to the right of alpha, this is positive. Oh, and notice that's another benefit. I don't have to consider this one at all, because this one is always positive. No matter what, that 4 is going to make that positive. So when you're to the right of alpha, this thing is positive, this thing is positive, so it's positive. This is actually, despite being intimidating, this is actually easier to analyze. What happens when you're between 1 and alpha? When you're between 1 and alpha, you're less than alpha. So this is negative, and this is still positive. So the grand total is negative. What happens when you're between 0 and 1? Something like a half. Well, 1/2 is in this range, so you're negative, and 1/2 is still positive. So what happens when you're between 0 and -1, like minus a half? Still negative. Now this is negative. 2 negatives is positive. What happens when you're between -1 and minus alpha? Still negative. And this is negative. So again, positive. See, when you're between -1 and minus alpha, that is still negative, and that's negative 12, so it's positive. Actually, I think I'm putting positive. Negative. Oh, I know. Where do you think it's negative?
At 0 and positive.
I bet you're right. Let's look at that again. I was probably, let's look at this again. That's right, because it shouldn't change. That's what the negative 1. Let's go between 0 and 1, like a half. That's negative, and that's positive. Negative, positive. So I made a mistake there, but actually, I noticed that this had to be some kind of mistake here because of the sign change here that shouldn't happen. Finally, what happens when you're to the left negative alpha? This is now positive, and this is negative. So I get negative. So it's concave down, concave up, concave up, concave down, concave up, concave down. So we have this, and this are points of inflection. Okay, let's see if we can take this apart. This one's got to come up. We'll look. Let's see, notice it's 0, 1, and minus 1. Goes to the origin, right? Because if you plug in 0, 1, or minus 1 here, you get 0. All right, let's see what we can do here. This is a 0, this one right here, the local min. You have a local max at minus 1, 0. And you have a local min, oh, about right here. And you have a local max about right. Everybody with me so far? This is about 1 over the square root of 5. Now, what happens here? Well, can somebody describe what's probably going to happen? So if these 3 points solve the problem, you point out actually that these 3 points, the derivative is undefined. Anybody can guess happening? Yeah. So, right. Let's see, what was our concavity look like? Concavity. So, let's take it up in here. What happens up to this first local max? It's always increasing, and its concavity goes down to up, sort of the last minute. Right? Alpha's over here somewhere. What happens at the first local max? Because it should go up to the local max and then down, and the derivative doesn't exist. My concavity is down. The concavity is down, and then it changes up at the last minute. Then it comes down. And we'll say, just kind of plug in, this is how what happens is here. So I see that the derivative right here doesn't exist, correct? What happens, what are you supposed to happen here? Well, I go through my local bin here. I go through 0, 0, and I increase up to this local max. So I increase all the way up to this local max, and my concavity goes from up, it's clearly up here, to down. What are you supposed to happen right here? Why do you suppose the derivative doesn't exist here? So what happens is the tangent line, notice how concave up, concave up, concave up, concave down. Actually, the tangent line works. And now when you pass it beyond this local max, it goes down to local min and then up, and the concavity stays down. And then concavity comes out of this, stays down, and then turns to up. So that's kind of an interesting one. You see the derivative failed to exist for 2 different reasons. You got a cusp at 1 and minus 1, and then a vertical tangent. Any questions? And by the way, I'm marking this. This is concave up. And this is concave. Okay, questions? All right, I'm gonna stay here until probably about 10 till 11. Your quiz will take it up to about 10:15. And